give an overview about the F-14's basic system, including engines, CCS, and whatnot. And in addition to that, before that, I'm gonna have a little talk about basic supersonic aerodynamics, so you kind of understand why we have systems like the wing sweep or the inlet ramps, and so what's the theory behind it. So again, this is our content. Sorry, I forgot. So first we're gonna do some basic supersonic aerodynamics. Then I'm gonna talk about the engines, the environmental control system, the fuel system, hydraulic system, and the electrical system. And it's gonna be accompanied by a couple of emergency procedures where it can be applied. But first, let's talk about supersonic aerodynamics and the so-called normal shock. Now, since air is compressible, we have these shock phenomena because it can be shown with a little bit of thermodynamic theory, which I'm going to spare you, that an airflow can only be decelerated from supersonic to subsonic speed via a so-called shock. So if we have, this is just an example, airfoil in 2D, and it's traveling, or the air is flowing around it at some Mach number, Mach 1, it is still lower than, M1 is still lower than Mach 1. The velocity behind the airflow will be the same as in front of the velocity, but in this part, on the upper side of the surface, it's going to get accelerated past Mach 1, because our airfoils, they accelerate the air as it passes the airfoil. So at some point here, the flow has to slow down from greater than Mach 1 to below Mach 1. And this is happening in this case with a so-called normal shock. It's basically in 2D, it's just a small line, and over that line are properties of air such as temperature, pressure, speed, of course, change rapidly. This band is not infinitely small, it is just very small, a couple of degrees of freedom of molecule travel wide, but it's very, very small. And again, over that so-called shock, our static pressure rises because the flow is kind of, it stagnates a bit and the pressure rises. But our total pressure, which is the static pressure plus the kinetical energy, it drops because the shock, it creates entropy, which means let's say it destroys usable flow energy. So we kind of lose energy with these supersonic compression shocks. The velocity goes down because it slows down, and of course the Mach number goes down. Our static temperature rises because as the flow gets compressed, it gets hotter. You may know that phenomena from basic thermodynamics. If you compress a portion of air, it's gonna heat up, and this happens here. But the total temperature, which is basically our static temperature plus the kinetic part, it stays the same because the shock, it doesn't create energy and it doesn't destroy energy, but it takes away energy which we can use with our aircraft, which is static pressure and total pressure. And thus our overall lift-to-drag ratio goes down because for one point we lose lift because we're getting a high pressure area here, and the drag increases because our total pressure goes down. So we basically lose usable energy, and this is called wave drag. So basically any drag that is created by this compressible phenomena, these shocks, is called wave drag. And this would be the situation at a sweep angle of 0, which means we have a straight wing. Now at some point in the 30s, I think, somebody came up with the concept of a swept wing. So we basically take our... before I come to that, I just wanted to show you how this develops. So we have a shock, and as we get faster, the shock moves backwards, it gets stronger, and on the underside we also get a shock because the air is also accelerated on the lower side of the airfoil, but slower than on the upper side. So on the lower side we also get a shock, and as we pass Mach 1, we're having 2 shocks at the back and a so-called bow shock at the front. That's basically the configuration you would see in supersonic flight. You can also see it if there's a lot of humidity. This is what causes these Mach cones. You have these because the pressure rises rapidly, and the moisture in the air condenses. Just to give you an idea how much wave drag does, so here's the drag coefficient, right, over the Mach number. And in subsonic flow, it stays roughly the same, and then it rises rapidly, like by about over 50%, as you can see here. So the wave drag is really a big problem for aircraft, because it creates just a huge amount of drag. And so therefore, people came up with the idea of a swept wing. And what we do is we take our straight wing and we just sweep it at a certain angle, let's say 45 degrees. Now what gives us this? Let's say our wing is, let's say air is flowing around that wing at some speed, and then we can decompose that vector basically in a component normal to the leading edge and parallel to the leading edge. And then we can say, well, the component that is parallel to the leading edge, it doesn't affect our aerodynamic properties. This is not correct, but as a first assumption, it can be valid for the mathematical formulation. So what we get here is, we have our airfoil, but now it's swept at the angle lambda, which is 45 degrees. And the velocity that basically is aerodynamically effective is now mam1 times cosinus lambda, which in the case of 45 degrees is 0.7. Which means that the airflow at the same m1 that we had in the previous example is not going to go supersonic over the airfoil, because again we are multiplying it by the cosinus of a sweep angle, and this way we can delay the onset of these compressibility effects, and this way we can increase the so-called critical Mach number. The critical Mach number is the Mach number at which this wave drag starts to rise, and the phenomenon is called drag divergence. So this is basically why we're using that wing sweep. By angling the wings backwards, we kind of reduce the effective speed, and this wave drag is kind of getting pushed back further towards higher Mach numbers. So this helps us fly faster, really. Yeah, exactly. It's below Mach critical. The next concept I want to introduce is the so-called oblique shock. This is basically shock that comes at an angle. Just we're gonna need that later, but just imagine this small setup. We have just, and again in 2D, we have just a channel, right? This is the floor, and then we have some wedge, which we just place into the airflow. We have some supersonic airflow coming here, and then this airflow is getting deflected by the wedge. And what happens is we're getting a so-called oblique shock. Again, this is a supersonic compression shock, but this time at a certain angle, and it slows down our velocity, but not necessarily below 1. So basically, let's say if this is 5, this can be 4. But if this is 1.2, this can be 0.8. It depends on a few factors. And these are, we define our shock angle beta, and then we define our deflection angle theta, and then we find that the shock angle beta is going to be a function of our free stream velocity m1, or free stream Mach number m1, and our deflection angle theta, which is a geometrical feature of whatever part we're looking at. Just a little bit of an example. This is a so-called beta-theta diagram, and it shows you for which configurations what shock angles are to be expected. So let's say we have, we're flying Mach 1.8, this would be this isoline, and we have a deflection angle of 15 degrees, and we're going to get two shock wave angles. One is about 52, and the other one is 70 degrees. And the difference is, the upper one is a so-called strong shock. It will decelerate the airflow to below Mach 1, while the lower one is a weak shock, and it's going to decelerate the flow to higher than Mach 1. This is an important thing, as I'm going to show you later, because these weak shocks, they destroy much less usable energy. So the strong shocks is something you want to avoid in your design, because they destroy a lot of energy that you can use as an example above. And now last thing, and the other perk of swept wing aerodynamics is the fact that when we travel over Tomcat at supersonic speed, our nose is kind of a wedge, right? It deflects the airflow, and this also creates an oblique shock, as in the example before. Now you can see that as long as the swept wing stays inside that cone, it's gonna see a lower Mach number than the free stream Mach number, which further reduces wave drag. Imagine if we had straight wings, which would protrude out of the Mach cone, we would get an additional shock at the edges of our wings, creating additional drag. And we kind of avoid that by having this 68-degree sweep angle. So that's basically it for the, oops, sorry, tapped out. That's basically it for the supersonic aerodynamic introduction. Just to reiterate, we have this wave drag, and to reduce the wave drag, we are sweeping the wings back to reduce the effective component. And also in supersonic flight, we have this oblique shock, which further reduces our Mach number. Now, swept wings have also a downside. So basically, they reduce the so-called aspect ratio, which is the ratio between wing span and wing area. And you want to keep that as high as possible, because if this ratio goes down, you're getting secondary effects which diminish your wing's efficiency, especially at high angles of attack. So you don't want to fly that configuration in subsonic regions, only when you're supersonic. So basically, usually you have to trade off between slow speed and controllability with thick airfoils, which create a lot of wave drag. And the Tomcat doesn't need to do that compromise. It can do both, because it can sweep the wings forward for maximum slow speed efficiency and sweep them back for supersonic flight. All right, any questions so far? You still with me?
Yes. Yeah.
Okay. Let's take a look at our engine. This is the GE F-110 afterburning turbofan engine. It has basically a couple of major components. The front one is our free-stage low-pressure compressor. It basically does two things. It creates a lot of thrust, because these fan blades, they blow air down the outer counter, which creates thrust, and they pre-compress air for the high-pressure compressor. The high-pressure compressor further compresses the air and feeds it into these combustion chambers. The combustion chambers burn fuel and create the energy necessary for the turbine. We have actually two turbines. You have one single stage high pressure turbine, and I'm not sure, I think it should be free stage, but anyway, and two are free stage low pressure turbine. Now, since these things need to run at different RPMs, they have each their own shaft. So we have this is combustion chamber. We have an inner shaft which connects the low pressure compressor to the low pressure turbine, and we have an outer shaft which connects the high pressure turbine to the high pressure compressor. So these two things can have different RPMs, which is necessary, and this makes them aerodynamically balanced, because the ratio between these two RPMs is not going to be the same throughout the envelope. Especially in idle, this may run at something like 20%, while this will be 70%, and as you approach mil power, they're both going to go to 100%, which still doesn't mean that the RPMs are equal. I think this one turns a lot faster than the LPC. Let's take a look, a bit of a more schematic overview. This is a cross section, and it's just the upper part, because the lower part is symmetric. So we're just not gonna look at that. This part is our 9-stage high pressure compressor. So basically this is our single stage high pressure turbine, and this is basically the shaft that connects these two. And the whole thing here is the so-called core duct, because this is where the core airflow goes through. Here, a bit of a naturalistic depiction. This is a picture, I think, of the actual compressor of the F-110. You can see it has little blades that turn and compress the air, and these get progressively smaller because the air is getting compressed and it loses volume, so the channel has to constrict itself. On the other side, you have the turbine. Not much to see here, unfortunately, because it has the shroud is welded on the blades, so you can see the blades, but it's basically a similar concept but reversed. And just to reiterate on just a tiny bit of how these compressors work, you always have, this is a single stage, you always have a rotor and a stator. You can't see the stator here because the stator is part of the shroud, so it would be connected up here. And the stator blades would go in between these gaps, which you don't see here. And we have some intake velocity, and we have the velocity of the rotational velocity. And if you add these two, you get a vector. And this is what basically the blades see. And they work like a wing, more or less. They create lift, and they first of all they create pressure, and then they rotate the whole airflow, right? So if you would look down the channel, these rotors they swirl the air, and what happens then? The stator blades they take the swirl out. So basically, the air would come in at this angle into the stator, and it will straighten out the flow, which will create additional pressure, because you don't want to have swirl flow, you want to have straight flow, which is much pressure as possible, and this is what the stators are for. They kind of straighten out the flow. And then you can see that the outflow velocity will generally be smaller than the inlet velocity, because you're compressing air, the density goes down, and continuity equation demands that velocity reduces. So then with the combustion chamber, again, nothing. I mean, it's also an art for itself to have these proper working combustion chambers, but it's just a flame that continuously burns and deliver the hot gases that exit here, and that the high pressure turbine takes to convert these basically chemical energy, or not chemical, thermodynamical energy to mechanical energy. Then we have our three-stage fan low pressure compressor, which is on the inner shaft here, and this is driven by the three-stage low pressure turbine. So basically, whatever energy is left after passing the high HPT, the LPT takes to drive the fan. And because this needs a lot more energy than this, the high pressure turbine drives is located next to the combustion chamber, where there's most energy, and basically the rest is used by the low pressure turbine. And like here we have the afterburning chamber, basically a long duct with an array of nozzles and sprayers that spray fuel directly into this chamber, which then gets ignited and delivers additional power. And lastly, we have the fuel control. So we have the fuel control in the combustion chamber, and the spray bars I talked about. And basically, the engine is only controlled by the fuel flow. I mean, there's several other systems that have an influence, but generally, the amount of fuel that gets into that combustion chamber governs the power output. This is why the fuel flow meter is a good indication of thrust. Let's take a look at what instruments we have in the cockpit. First of all, we have our RPM, EGT, and fuel flow. The RPM is the RPM of the high pressure compressor, not the not the LPC. We don't have information on that, but we don't need it, because this thing is more critical than this thing. Because by the time this overspeeds, this will already have disintegrated. So we're interested in exactly the RPMs of the high pressure compressor. DGT is the temperature sensor. Oh, just a second.
The Admiral is intervening.
Oh well.
So okay, exhaust cut temperature, right? So these turbines, they're made of some kind of alloy which is very heat resistant, but not infinitely heat resistant. And we want to know what temperature is basically around the turbine. We only measure the exhaust gas temperature behind the three-stage LPT, because the temperature here correlates strongly with temperature here. And there's certain limits, which are indicated here, which is 935 degrees. If you exceed that value here, chances are high that you're exceeding the maximum thermal stability of the high pressure turbine blades, which means they will start to deform, they will start to fly out the casing as things that you don't want to happen. So basically, whenever you see this here rising above these marks, you want to reduce your thrust. And lastly, we have the fuel flow, which measures our fuel flow to the combustion chamber. It does not measure afterburning fuel flow, unlike in the F-16 where it does. But there's really no point in measuring this because it would go through the roof. So it measures only the fuel flow in mill power or of the core engine, so as to say. One more thing about these bypass duct afterburning engines is that they have an important advantage over the early jet engines, which did not have these bypass duct, because the early jet engines like the Phantom, the afterburning chain had to work with whatever oxygen was left after the air passed through here, which was probably not a lot. And the new engines, and already in the Tier 30, the afterburning chamber could use all the oxygen that came through the fan duct, which gave it a lot more power. This is why these engines are so powerful compared to older engines. They just have a lot more oxygen to work with in the afterburning chamber compared to the classical afterburning turbojet. Alright, this is basically our engine, but the engine itself is not enough. It has several accessories that the engine itself needs, but also our aircraft needs. One is the air inlet control system, left and right. We're going to talk about that in a second. Then move to right, left and right exhaust nozzles. Also going to come to that. These things basically increase engine efficiency, or in the case of the DCS, it makes it even possible that the engine runs at supersonic speed. This is the augmenter fan temperature control, which is a fancy name for basically digital engine control. Today you would call it FATIC, I think, and it basically takes care of the fuel control of the afterburner, makes sure that the engine doesn't stall with rapid throttle movement, all these things. It's basically the digital engine control. For example, the TF30 F-14A doesn't have that. It only has the mechanical engine control, where you have a very complicated hydromechanical device that regulates fuel flow based on your throttle setting. And the F-14B is a bit more advanced. Then you have the left and right generators, which they are mechanically driven by the accessory gearbox, and they provide the electrical power. Then we have hydraulic pumps. The left one powers the combined hydraulic system, and the right one the flight hydraulic. We're going to talk about that later too. And each engine has its own engine-driven fuel pump. By the way, this is not the pump that is that's in the combustion chamber. This is basically an additional pump that kind of pre-pressurizes fuel before it gets into the combustion chamber fuel pump. So you have basically two pumps. The one that's the one that kind of takes fuel from the fuel lines out of the tank and then sends it to the fuel control pump, which then actually pumps fuel into the combustion chamber. Let's take a look in the AICS. We need that because remember when I talked about wave track and how it negatively affects the airfoil? Well, it does the same to the engine, which also has these little airfoils, as you've seen there. So you wanna prevent supersonic flow in your engine at any cost. So you wanna make sure that the air that enters your engine is well below supersonic, because as we have seen, the air that the airfoil sees is an addition of the circumferential velocity and the inlet velocity. Now at subsonic speeds, this is not a problem because first of all, part of the flow is taken out, and then we have this diffuser which increases the cross section, and this in turn reduces flow velocity. But as we get transonic, we need these ramps to slow the air down. So the first part is when you're transonic, we have a bit of constriction here, which accelerates flow, and then at some point we're having a normal shock, similar to what we had with the airfoil. And that normal shock it will reduce our inlet velocity below Mach 1, and the subsonic diffuser will further reduce the velocity to acceptable levels. Now, when we're supersonic, we have a configuration of oblique shocks. Now, let's take a look at the front. As you remember, the angle of the oblique shock is a function of the deflection angle theta and the inlet Mach number. Now, here the deflection angle is fixed. This is basically the forward leading edge of the air intake. So we're getting here some kind of angle. The second deflection is a function of the position of the first ramp. This is the first ramp. It can move up and down. The third shock is going to be a function of the position of the second ramp. This is this part. And the fourth and last shock is a normal shock, so it will be always normal to that surface. Now, as we travel, or as we change our speed from, let's say, Mach 1.5 to 2.2 or 0.7 or even 2.0, these shock angles would change unless we adjust these ramps, because we want our four shocks to focus outside of our duct. Because if they were to go something like this, if they would cross each other within the duct, we would have a lot of bad aerodynamical effects happening here. So we want to focus all four shocks outside of our duct. And to do that, we need to position our ramps according to a special pre-programmed schedule that takes into account Mach number and also angle of attack. This is why each AICS controller has its own angle of attack probe on the left and right side of the aircraft. Because as you can imagine, if you're rolling, let's say you're rolling left, the left engine is going to have a higher angle of attack than the right engine. Now, what do I want to say? Yes, right. One last thing. This is a pretty, let's say, complicated arrangement, and not many aircraft have this, even fighter aircraft. There's also many aircraft with a static inlet setup, such as the F-16 and F-18. So technically, you can have some static geometry that does a one-size-fits-all approach. So whatever your Mach number, it's going to accelerate your flow to subsonic speed. However, it will do that inefficiently. The stronger your shock becomes, the more energy it takes out of your flow. And ideally, what you want to have is you would want to have an infinite amount of infinitely weak shocks, and weak means that the change in Mach number is infinitely small. And this way, you could transform all your kinetic energy into pressure energy and not lose any energy. Now, this is technically not possible, but what the F-14 engineers settled for is 4 shocks, and you have 4 weak shocks. 3 weak shocks and a normal shock. And this basically makes this transition from supersonic uncompressed flow to subsonic compressed flow as efficient as possible, which means not losing energy to entropy. So this is basically our AICS and why we need that, and why without that system we probably wouldn't be able to reach anything above Mach 0.2 or something, Mach 1.2. Let's take a look at the engine nozzles. This is another thing that is designed to maximize our thrust. Now, as you may or may not know, the thrust that an engine produces is a product of the mass flow that goes through the engine and the exhaust gas velocity. Now, the mass flow is more or less fixed because it depends on our compressor size, fuel flow, and whatnot. But the engine exhaust velocity is something we can influence. And the way we do it, we're building a nozzle here, because the nozzle, it constricts the available cross-section area. By the way, the upper part is the nozzle in the closed position, and the lower part is the nozzle in the open position. But let's first focus on the closed position first. This is the position you're going to have in flight whenever you're not using afterburner. So air is coming here. So here's our afterburning chamber. We're getting gases. They're getting deflected and constricted, which means they have to accelerate, and then they accelerate out and maximize our outflow velocity and thus maximize our thrust. And now, if we didn't have an afterburner, we wouldn't need all these configurations. We would a fixed geometry would do, but we have an afterburner, which means that the pressure ratio, or the nozzle pressure ratio, which is the pressure behind the nozzle and the pressure in front of the nozzle to the pressure behind the nozzle, which is ambient pressure, is going to vary by a lot. Because the more afterburning fuel we pump into the combustion chamber, the higher the pressure before the nozzle will get. And if we would use the same geometry, our gases would be what is called underexpanded, which means they would still have energy to accelerate further downstream as they exit our nozzle, which means that we would have wasted energy that we could potentially use to maximize our thrust. And to prevent this, we have this variable nozzle geometry. And what it does, it is a convergent-divergent nozzle, which means that it has a convergent part and a divergent part. And this is important because at some point, the gases exiting here will be so fast they're going to reach supersonic speed. And if the flow becomes supersonic, it cannot be accelerated using a constrictive geometry anymore. Instead, it needs to have an expanding geometry. So what happens is we're getting high pressure, high velocity flow here, which is accelerated to Mach 1 exactly at that point where the divergent flap begins. And as it enters the divergent part, it accelerates even further to above whatever speed. And this configuration will depend on our pressure in the afterburning chamber, on our ambient pressure, on our velocity, and on a lot of things. And to find the optimum configuration for the full flight envelope, we have this variable exit nozzle system, which again maximizes the thrust and is another mean to increase thrust without actually changing something within the engine. So this is the engine part. I hope you're with me so far. And next, we're gonna talk about the engine controls that we have in the cockpit. So first, I talked about the left AICS and right AICS. They are mostly automatic, but we have these switches on the left vertical panel, the left horizontal panel. They can either be in auto, which means they work automatically. They will adjust the ramps according to schedule, or we can put them in stow. And stow means they're going to retract all ramps to the stowed position. Next thing, we have our engine mode selector, which is also on the left horizontal panel next to the throttle. And what we can do with that is, I talked about the AFTC, how this is an electronic engine control. Well, we have a backup mode. In case this is basically a computer, in case it fails, we have a backup mode, which uses old hydromechanical control system similar to the F-14A. And we can either, the transition can happen automatically if the AFTC detects fault, or we can force it into sec mode. This is called surprise. Basically, use digital engine control, and sec for secondary means use backup. And we can go in sec mode manually if we wish to. Basically, one scenario would be a runaway throttle. If for some reason the RPM increases, although the throttle isn't idle, you would go to sec. Another scenario is if you're trying an air start and the air start doesn't work for whatever reason, you're going to try an air start in sec again, because in sec the windmilling RPM may be a little bit higher. Let's take a look at the warning lights that are associated with the engines. Here are the left inlet and right ramps. Left inlet lamps say that there's something wrong with the AICS controller, which is also a computer. And the ramp lights basically says that the ramp position disagrees with the commanded position. So basically some kind of mechanical fault within the ramp system, among other things. Basically they can mean a lot, but these are the most practical ones. Oil pressure is self-explaining. The minimum oil pressure is 15 psi for the F-110, and whenever it goes below that on either engine, this light comes on, and then you're going to check the engine oil gauges to find out which engine is affected. This is the engines, left and right engine sec lights. They come on whenever you are out of primary engine control mode. So again, this can either happen automatically if the controller fails, or if you flip the switch. Whenever the engine is in sec, these lights will come on. Next, we have left and right oil hot. Again, self-explanatory. Left or right oil is hot. We don't have a temperature gauge for the oil, but we have these little lights which come on. And left and right fuel pressure. But basically, we have a pressure sensor. After the engine-driven pump, again, this is not the one that pumps fuel into the combustion chamber, but the one that is sucking fuel from the fuel lines and pushes it into the fuel control pump. And if that sensor senses that fuel pressure is low, these lights are going to come on. And what this means for you as a pilot, we're going to talk about now. So here for the S control failure, what you want to do is you want to put the ramp in stow and you want to reduce the Mach number below 1.2. If you go faster than that, the air that enters the engine might become supersonic and your engine will die. All temperature high, what you can do is you push the throttle to 85%, which increases basically the rate at which the oil system works, and maybe it will cool the oil better, maybe not. But if you push it to 85% and it doesn't go off within a minute or so, you have to turn the engine off. Fuel pressure, basically not that bad, but you want to fly below 25,000 feet, and you do not want to use afterburner, and basically stay in cruise power, which is something like 45,000 pounds max at altitude. Oil pressure low, that's if you see that, you have to turn the engine off. I mean, again, as operational necessity dictates, if you're in a dogfight and this comes on, you're not going to turn your engine off. You're just going to fight until you either win or your engine dies, whichever happens first. And engine and sec mode, we're going to cover that in a little more detail because there's a little bit more to it. So whenever we're in engine sec mode, this can happen in manual or automatic transition. So if you take battle damage, sometimes the engines would go into sec mode, because I'm not sure if this is realistic, but in DCS it happens quite a lot. If you take a hit but can still fly, chances are good that you're in sec mode. Indicated by the sec lights. And what happens is you do not have afterburner in sec mode because the afterburner fuel control is bound to the AFTC. The nozzles close fully. So this is basically not a problem for you as a pilot, but when you're on the ground, you should be aware of it, because if at some point heat blur gives us a good ground friction model, being on the ground with nozzles fully closed and idle is gonna make your aircraft move pretty fast. Power output is reduced again. This is real life stuff. I think in DCS it doesn't matter, but in real life the output power in sec mode is less, even in mil power. So not counting MB, just baseline power will also be lower. And the stall margin is reduced again. Don't think this is something that DCS models, but high angle of attack, rapid throttle movements, stuff like that can make the engine stall. Not a big deal in primary, but in secondary this can become a problem. I think what DCS does model, if you try to go supersonic in sec mode, your engine will start to pop, which indicates compressor stalls. But which shouldn't happen, because since you don't have afterburners in sec mode, going supersonic is going to be difficult. Right, so far for the engine controls, and the next is the environmental control system. A very important system, which I think gets a bit of neglected. But it is important because it delivers, for example, air for cabin pressurization. The F-14 is a pressurized cabin. Nevertheless, we always wear oxygen masks in case of a rapid decompression. We don't want to pass out, so we always use them, but technically we wouldn't need these masks. This is also why this hypoxia effect, which DCS has, is unrealistic, because technically you wouldn't even need an oxygen mask even at 40,000 feet, because the Tomcat, like any normal aircraft, has a pressurized cabin, but so be it. Next is equipment cooling. We have a lot of analog tech which consumes a lot of power, and this power is dissipated into heat, and this needs to be carried away from the avionics compartments. So equipment cooling, especially the OC9, the transmitter, the whole control blocks and stuff, they need cooling, and the ECS provides for that. Sealing, we have, if you ever paid attention, when the wings are fully swept forward, right, the gap in the fuselage where the wings would retract when you sweep them back, they are sealed by a special. So they are sealed by a special system of bags, and these bags are inflated with pressurized air. And also the external tanks, you can see they are on the most bottom part of the aircraft. Sorry. The tanks are located on basically the lowest part of the aircraft, and you need to pump the fuel of the tanks up into the fuselage. And the way this happens is there's always compressed air being pumped into the external tanks, which creates the pressure head that we need to pump for the fuel out to flow out of the external tank into the fuselage. So let's see basically how this works. We have the left and right engine, which compresses air, and we can take part of that air through certain valves and route it into the so-called system of heat exchangers. So we have basic compressed air at about 200 degrees Celsius, something like 400 Fahrenheit. It goes to the special duct and goes into a heat exchanger. Actually, it's two heat exchangers, and they reduce the temperature of that air to be usable for our cooling and cooling tasks. And from these heat exchangers, the air is distributed into the cabin for pressurization, the avionics bay for equipment cooling, the OG9, which has its own system of cooling because it is liquid cooled. So there's basically a separate cooling system for the OG9 and the Phoenix, especially the old Phoenix. They have their own cooling system. And the gun, because we have a gun gas purge system, which uses compressed air to expel gun residue gases out of the compartment. And then we also, a part of that hot air is cooled only partially. So we have basically a duct of cool air and a duct of hot air. And by mixing these two, we're going to get the cabin pressure that we want. And what also happens is we use the hot air to seal our wing backs, to clean our windshield, and to pressurize our external tanks, which conveniently also heats up our fuel. In addition to that, we have several valves which control the flow. We can so within the engine itself, there's a left and right bleed valve, which basically shuts off or opens, taking off air out of the compressor, and then we have a common valve which shuts down airflow to the heat exchangers. And lastly, we have a ram air scoop, which is basically a little scoop that comes out of the right glove when a certain switch is pressed, and this acts as a backup air source in case this stuff here fails, but we still need to at least cool the avionics. We can use ram air. Now let's see what controls we have for that. That's the ECS control panel on the right horizontal panel. This is our air source, and this is our ram air switch. That's basically the important ones for this example. The normal operation is it is in both engines, which means both bleed valves are open. The flow to the heat exchangers is provided, and the system operates normally. Now we can partially shut off the system by going into right engine, which means the left bleed will be shut down, and the whole system is going to use right engine bleed only. You would do that if you, for example, if you want to air start the left engine, or if there has been a fire in the left engine, would want to shut it down. Same for the left engine, just the other way around, right valve shuts down. Now we have the off. Off completely shuts down, closes all valves. It closes the valves to take out bleed air, and it closes the pathway to the heat exchangers. You would do that whenever an engine fire is detected, because it can be that a part of the engine fire warning also means that these ducts may have a leak somewhere. So you want to shut it off if you get that warning. But what you do is you put the ram air switch into increase for at least, I think, 70 seconds. This deploys the ram air scoop, and the ram air scoop will provide cool air to the avionics bay and to the OG9. So basically, with this mode, if for whatever reason we have to shut off the primary air source, we can still use the backup air source to keep flying and navigating and maybe even fighting. But we lose our cabin pressurization, we lose the gun, and we lose wingback seal and external tank pressure. The last thing is RAM. This is kind of a mixed mode. So what it does, it retains the bleed. So the left and right engine bleed air valves remain open. However, the pathway to the heat exchanger is partially blocked. So what happens is that only the hot air portion of the heat exchangers work, and the difference to the off mode is that we don't have cool air from the engines, but we have hot air from the engines. So what we can do then is we can still heat up our cabin, and we can still use the windshield. However, we still don't have a gun. The reason why I would want to do that is there's basically two heat exchangers in the aircraft, and if you know one of them fails, or there's if you know basically there's a problem with the heat exchange, but you know that the engines and the engine ducts are good, you can go into the RAM mode, and you retain basically more capability than if you were in the off mode. But this is basically a rare occasion, because you can never be absolutely sure that there's nothing wrong with this, and only something wrong with this. But this is basically what these 5 switches do. One more restriction is if you deploy the ram air scoop, I think you have to stay below Mach 0.9 or 350 knots indicated, because it would just tear the ram scoop apart if you were to go faster. So then a little bit of an overview over the warning lights. There's not much to that. The left one is in the rear pit, the right one is in the cockpit, in the pilot cockpit. Any of these means that the coolant that is used to cool the Phoenix is above certain temperature threshold. If the rear sees that, he places the liquid cooling switch into AUG9, basically shutting down the Phoenix missiles. Yeah, this is all you can do, because otherwise you would risk a fire or something, or damaging the equipment. If this comes up, this means that the AUG9 cooling system is overheating, and this means WCS switch off, because you don't want to overheat your AUG9. None of this is modeled right now, but I think Heatbird said that at some point it will be modeled, so you probably want to get used to have a look at these indications if you're real. And for the pilot, there's just a bleed duct valve light, and see that there's temperature sensors along the bleed duct, which is this part. Basically, this part is within the engine compartment, which is behind the titanium firewall. This part is outside of it is within the fuselage, outside of the titanium firewalls, and the duct has a lot of sensors placed around the duct, and one of these sensors goes, I think, beyond something like 400 Fahrenheit or something. This will come on, and if you see this, you would want to shut down at least this, but ideally you would turn the system off altogether, because if you don't, you risk overheating things in your fuselage or even a fire. And if you do that, yeah, air source off, ram air increase, and here, so it's just 300 knots, not even 350. So this is this is basically our ECS and what we can do with it as a pilot. And as we're going to take a look at the fuel system, which is quite complex in the Tomcat, but also quite hands-off. There's really no controls, just a few, and it operates completely automatically, which is very convenient, especially if you consider the aircraft is from the 60s. They've put a lot of thought in that. So let's start with a bit of an overview. We have the left and right feed tanks. The left one holds 1,500 pounds, and one is 1,600. And the engines draw fuel from these tanks only. So basically, the left engine feeds from the left tank, the right engine feeds from the right tank, and it's in these feed tanks where these engine-driven pumps are located that I talked about earlier. Next, we have the forward and aft fuselage tanks. They hold expected 4,700, 4,400 pounds of fuel. And the way they're connected is the after fuselage tank feeds into the left feed tank and the forward tank into the right. Then we have the wing and external tanks. The wing tanks each hold 2,000 pounds and the external tanks 1,800 pounds. And the way these work is the external and wing tanks, they both feed into a common line, and then they feed into the feed tank. Now, this is important here because if you're, let's say you have 20,000 pounds of fuel and you see you're down to 16,000. Now you would think that, okay, nice. If I already consumed 4,000 pounds of fuel, this means that the external tanks are empty. Well, no, this does not mean, because these feed simultaneously. Probably have still 1,000 pounds of fuel left in the external tanks, and if you were to drop them at this point, you would just lose fuel. So remember, these feed simultaneously. This is important. Now this is the normal mode of operation. We have a left system and a right system, which are completely isolated, and each providing fuel. The order is first the external tanks are getting sucked dry, then the after or forward fuselage tank is getting depleted, and then you have whatever you have left in the feed tanks. But we also have some backup systems and controls in case we have failures. Now let's take a look at the controls. So, sorry. The indications are a bit slim. We have the bingo warning, which is, you know what bingo is, and left and right fuel low. I think this comes on with the respective left or right feed tank goes below 1,000 pounds. Don't quote me on that. Oh, sorry. So, and right here we have the fuel control panel, and it's basically just these four switches. So this is the feed control. As I said, normally the systems are isolated, but you could force both engines to draw fuel either from the aft or the forward system. This one is controls the fuel display. We're going to talk about that later. Refueling probe. Fuselage extended means that the wing tanks will not be refueled. If you put it in all extended, which means everything will be refueled. Also, the reason for a lot of bug reports when people did not know how this works. Wing external transition basically controls whether we want to take fuel from the wing and external tanks or not, and the fuel dump switch. Let's take a look at the indicator. Since we have these two tapes, and they will always show the quantity in the right and forward and aft and left system respectively. Then we have these dials here, and they will show a value dependent on the fuel quantity switch. Now, in the normal mode of operation, they're going to show basically when the fuel quantity switch is in the normal position, they're going to show the fuel quantity in the left and right feed tanks. Don't ask me why it's 1,800 and the Tomcat, in the DCS Tomcat, it should be 1,500.
Doesn't it contain in the pipes or something?
Yeah, but I don't think they have 300 pounds in the pipes or something. But it doesn't matter. It's if you put the control switch in external, just to reiterate, I'm talking about this switch here, which is three position, feed, wing, and X. If you put them in X, it's going to show you the amount of fuel in the left external tank, and if you put it in wing, it's going to show you the fuel in the left wing tank. And the same works for the right system, respectively. Now let's see what happens if we put this switch here in the forward position. If we put it in the forward position, the fuel flow from the after fuselage tank to left feed tank stops. The wing and external fuel lines get connected into one fuel line, and the so-called sump-tank interconnect valve opens, and this basically connects the left and right feed tanks, and the flow direction, which here is in the left direction, but generally the flow direction will be governed by whichever tank has more fuel, because this is purely pressure head transition. So if we have, let's say, 1,600 and it's 1,000, the fuel level in this tank will be higher, which will create a pressure difference in respect to the left tank, and fuel will flow in here until that pressure difference is equal. But generally, what this means that we will not take any fuel from the after fuselage tank. Let's see what happens if we put it in the afterfeed. Well, basically, same thing, but this time the forward fuselage is getting isolated, and we're connecting both wing external tank fuel lines, and this time the fuel will feed basically from the left feed tank to the right feed tank, but to the respective engines too. Now, why would you want to do that? Let's say for whatever reason you have a fuel imbalance, and there's a directive that says if your fuel imbalance is more than 1,500 pounds and you have, I think, below 5,000 pounds left, you need to equal out the after and left fuel levels, and you could do that with that switch. So basically, if you have too much fuel on that forward tank, you put the switch in aft and draw fuel until both tapes are equalized, and you then put it back in norm, for example. And here's a bit of a more naturalistic depiction of where the tanks are located. So this is our wing tanks here. This is the forward fuselage group connected to the right feed tank, and this is the aft fuselage group connected to the left feed tank. And you see these are the left and right feed tanks are basically two tanks. You have the box beam tank, which is this thing here, and you have the sump tank, which is below, which you can barely see, but this is the sump tank. And in that sump tank is the engine-driven fuel pump. And if you wonder how this transfer works between the tanks, because there's no fuel controls for any kind of fuel pump, this is done using motive flow. So basically there's pipes running around all the tanks, and they use the Venturi effect to basically draw. So basically you pump fuel from this tank into this tank to get more fuel back. Basically this is how this motive flow stuff works. And you only need one pump per side for all of this transfer to work, and this is the engine-driven pump. So you have the engine-driven pump, this is the motive flow pump. You have one motive flow pump, which basically provides the fuel transfer between all these tanks. And there's no control for that because it's always on. And this makes the system pretty much hands-off, and you have a lot of sensors which close down transfer if a tank is empty and whatnot. What I've heard from real-life cases that at one point a sensor which tells the transfer, I think, into the left feed group failed, and the after fuselage kept transferring into the left feed group and overfilled it, and this caused a bit of an emergency. The fuel system was reportedly a bit troublesome, but it's still quite impressive because it's completely hands-off. You don't need to manage anything except for fuel imbalances, which should never happen actually. The second last thing we're going to take a look at is the hydraulic system, which is again pretty complex, but almost completely hands-off. Works all by itself. Let's see how that works. We have the left and right engine, which drives the combined hydraulic pump and the flight hydraulic pump. These pumps distribute hydraulic power to the actuators of the left rudder, the left step, the right rudder, and right step. And you can see both pumps or both systems deliver to all four control surfaces. Basically, these are our main control surfaces, the steps and the rudders. But then the combined system also provides power to the left main flaps, right main flaps, left and right aux flaps. The aux flaps are the inner flaps, which basically only drop down if the flap handle is, I think, below 30% or something. It also powers the left and right inboard spoilers. For the outboard spoilers, you have a separate outboard spoiler motor. This is an electrically driven pump, which is not connected to any of this. It's its own pump, and it powers the outboard spoilers. And the reason for that is you're more likely to take damage on the other side of the wings, and you don't want these lines to be pierced by shrapnel or whatever. So the engineers decided to basically make the outboard spoilers standalone. So because if this was connected to the rest of it, any leak in this system would basically compromise the whole system. But this way they're isolated. Even if this was to completely fail due to whatever reason, our main hydraulic system will not be impaired. Then we have our left and right rams. As you remember, you have these actuators that position the rams, and they are hydraulic, and they work from their respective sides. So the combined side is the left side, it powers the left DCS, and the fly side is the right side. But, however, both sides drive the wing sweep motors. If one of these pumps would fail, you would only have half the wing sweep rate. And then finally, you have some auxiliary stuff like the speed brake, the gear, the hook, the gun drive, the air-to-air refueling probe, and of course the brakes. Now this is the normal mode of operation if everything works, but if we're to have an emergency, we have the so-called bi-die. The bidirectional pump can, in case one of these pumps fails for whatever reason, for example, if the engine is shut down, you can transfer hydraulic pressure from, for example, if the flight pump goes off, you can use the bi-die to transfer hydraulic pressure from the combined system to the flight system. That wouldn't be that interesting, but which is far more interesting, if your combined pump dies for whatever reason, which powers all of that stuff here, you can still use it by transferring flight pressure to the combined system using the bi-die. The next thing is the backup flight control module. It's a little electrically driven hydraulic pump which only powers the left and right rudder and the stabilizers. So basically, if for whatever reason both pumps have died, but the hydraulic system is intact, so you have no hydraulic leaks or whatever, you can use the backup flight control module to keep the aircraft controllable. Of course, the control responses will be bad, but it will keep you flying. And what we also have is, if for whatever reason the combined system fails, the left and right main flaps have another backup mode by using outboard spoiler module power to operate the left main flaps. So whenever the combined system fails for whatever reason and you cannot transfer power from the flight side, you can still use the main flaps because it will use outboard spoiler power. This transition is automatical. There's no switch for it. Whenever the combined pressure goes to, I think, below 1000 or something, this will automatically kick in and provide you with flap control, which is important for something like landing. And lastly, we have the hand pump, which is to the left of your seat. And you can basically do two things with it, depending on the position of the AAR switch. If the AAR switch is in off, you're gonna pump up the hydraulic pressure accumulator. The brake pressure accumulator. The brake pressure accumulator, you have a gauge for that. Below the HSD, behind the stick, there's a little gauge. If you ever wondered what it is the brake pressure accumulator gauge. The one is the emergency brake pressure, which is a nitrogen filled nitrogen fueled stuff which cannot be charged, but the normal pressure accumulator, it can be charged with the hand pump. So if you have a complete hydraulic failure, but you're still flying because you have the BFCM, but you can see that your brake pressure accumulator has depleted, which means you'll not be able to brake, you can use the hand pump to pump it up and get some braking action. If the AAR switch is out of the off position, the hand pump will power the AAR probe. So again, everything died, but you still have the BFCM, but you're low on gas and you want to refuel. What you can do is place the AAR switch into fuselage or all extended, and then pump the pump, and the refueling probe will come out. And this works in DCS, by the way. And lastly, this is basically, so what we talked about now is how to operate hydraulic stuff if we lost hydraulic pumps. And the last thing is, what can hydraulic pressure give us besides hydraulic movement? Well, this is the emergency generator. The emergency generator is a hydraulically driven generator which powers our most essential equipment. It is connected to the combined hydraulic system, so it will only work if we have pressure here. And this emergency generator, in case we have a dual generator failure, there's no battery on the F-14. We only have the generators, and if they die, we're gonna have electric power unless we use the emergency generator. And this emergency generator, I'm gonna talk about that later, provides vital systems. But let's take a look at the controls first. This is our hydraulic pressure gauge. It shows the pressure, the output pressure of the pumps actually, of the combiner. This should be a B. I think it already is. I should update that, but it used to be a comp for a long time, which is wrong. Now what we have here is the spoil, and this shows us the status of the output spoiler module. Now it can be on or off. Why can it be off? Because if you're underground, this is an electric motor which produces a lot of power and produces a lot of heat, and you need air flow to cool it, which you're not gonna have on the ground. So on the ground, this will be off, and so will be the outboard spoilers. It will only come on when you lower the flaps. So once you lower the flaps and you're hooked up on the CAT, part of the checklist is to check whether this thing is on, because it is important for your outboard spoilers. Then we have the emergency flight hydraulic system. So sorry, I should have remembered that. Yes, the emergency flight, which is the backup flight control mode, it has two modes, high and low. The low mode is has no limit on operation, but the high mode, which you want to use for landing and air refueling, has a limit of something like 20 minutes. And it is controlled by this switch here. So it can be an auto. Auto means whenever both of these drop, I think below 1000 dB FCM will automatically come on. You will hear it in the cockpit, which is unrealistic, I think, but you can hear it in DCS. And it will provide power to the control surfaces. And if you're doing air-to-air refueling, and if you're committed to land, you can put this in high, which will make these flag come on, and you get better control authority. And last thing is the hydraulic transfer pump. That's the bite I'll talk about. You can either leave it in normal, which means it will automatically transfer hydraulic power from one side to the other side, or you can shut it off. One reason for shutting it off would be if you know one side, so let's say you have battle damage and something pierced through one of the lines in the fuselage and the combined system is running dry, but the bite will still try to build up pressure using flight hydraulic pressure, and to just prevent that, you put it in shut off, because there's no point trying to pressurize a system which is lost in its integrity. All right, one more thing I wanted to mention. In case of a combined system failure, so basically if this pump has failed and our BiDi also isn't helping us, there are several systems that will not be available. This is no normal gear extent. If you still want your gear, right-click on the gear handle, which uses a backup system, which uses compressed air to. That's why they call it blowing down the gear. So basically, in a real aircraft, you would push the lever in, twist it by 90 degrees, and then pull it out with a lot of force. And this manually opens a valve in a nitrogen bottle and the forward wheel well, which then opens a pathway to that nitrogen to, forcefully push the gear down and unlock the locks and all stuff. You will not have nose wheel steering though. In any case, you will not have normal hook extent. This is why you use the emergency down. Again, I think right-click on the handle and it will come down. You will not have inward spoilers or DLC or aux flaps. Especially this part is important. If you're used to use a lot of DLC in the groove, which you shouldn't anyway, but you're not going to have DLC. And also you're not going to have aux flaps, which means that your approach speed will be higher. Yes, I'm not going to have any speed brake. Keep that in mind. And you don't have normal AR operation, but you can use the hand pump for that. Also no gun. No normal brakes. I had about anti-skid doesn't matter in DCS. Alright, so we're almost through. Last thing is just a couple of words about the electrical system. Electrical system, as I said, left and right generators powered by the accessory gearbox, and these power the left and right AC bus, so alternating current. There is a bus tie. In case one of these fails, the other generator can power both buses. Also, you have external power which ties in into these two. So if you're on a cold start, you're not going to have any of these, but you're going to have external power, which is going to power through that bus tie, power both buses. Then you have the left and right transformer rectifier, because you also need DC current for all kinds of things. And to have that, each AC bus has its own transformer rectifier, which powers the left and right DC bus. Again, you have a bus tie, which in case one of these fails, the other one's going to take over. Then you have two essential buses. An essential bus is basically a bus which powers the most essential equipment, and it distinguishes itself from the normal buses in that these buses have a backup power source, and that backup power source is the emergency generator. As I talked earlier, we have an hydraulically driven emergency generator which will power essential buses 1 and 2 for AC and DC power. So normally these buses are powered by the left AC and DC bus, but in case we lose generators in flight, we're still going to have this to at least power the essential buses. Let's take a look at the controls and indications. There's not much to say. We have a left or right generator, which means that the respective generator is not working. There's not much you can do about it. You can try to put the generator switch into off reset and then turn it back on, and hopefully it comes back online. But if it doesn't, you lost the generator. This is no big deal because one generator can take the load of the whole system. So basically losing one generator is not a big deal. First, transformer rectifier means that one of these has failed. It doesn't tell you which one because it doesn't matter for you. Usually, when I'm a bit unsure about in DCS, this comes on when you're on external power. However, which you shouldn't be since external power powers above us. But anyway, this means one of the rectifiers has failed, and for whatever reason. But again, there's nothing you can do about it. This is really just informative. Here's a control panel. You can turn the generators off or on. Sorry. You can turn the generators off or on, and you can also test them. But I don't think this is this does anything in DCS. But depending on if the light comes on and test position, you can deduct what kind of failure you have in the system. But what is important is the emergency generator control. So it usually it comes off automatically once you lose both buses. But you might want to shut it off. For example, before you shut the aircraft down, you turn the emergency generator off, because if you leave it on and turn off both engines, the emergency generator is going to kick in. You don't want to have that during a shutdown. So when you shut down the aircraft, make sure to put this in off before shutting down the engines. One thing that I wanted to mention briefly: what equipment is retained with a dual generator failure? Basically, what is powered by the emergency generator? We retain our flight instruments because most of them are pneumatic anyway. We retain our fire detection and protection system, which is important for protecting us from fire. The VHF radios, they also keep working. The IFF transmitter keeps working, which is also important. The engine ignition is also part of the essential equipment. This is important. If we have to relight an engine in flight, we can still do it even if we don't have generators. Instrument lights remain on, particularly important for night flying. The SAS, the stability augmentation system, is also remains on, important for dogfighting or landing. And our flaps, nose, steering, speed brake, and inboard spoiler controls also remain functional. On the AUG-15, which is the source management system, remains fine, so we can still jettison stores. We can still jettison stores if we wish to, even if we have a dual generator failure. Alright guys, that is it. Thank you for your attention, and I hope you enjoyed it, and see you in Nevada.
Thanks, man. That's a lot of information.
Awesome.
Thank you very much. That was cool.
Thank you very much.
I wish I was here from the beginning. That was very interesting.
I recorded that, so it's fine.
Alright.
Alright, guys. See you around.
Alright, have fun flying.
Fine, guys. Hope you enjoyed that presentation. And I hope I will see you next time. Fly safe.